sklearn, manifold, locally linear embedding. Description: Locally linear embedding (LLE) is a nonlinear dimensionality reduction technique that seeks to preserve local neighborhood relationships in the lower dimensional embedding. It assumes that each data point can be linearly reconstructed from its neighbors. LLE first finds the local neighborhood for each data point and then computes the weights that linearly reconstruct the point from its neighbors. Finally, it seeks a lower dimensional representation that preserves these local reconstructions as much as possible. Inputs: X. The input data is a NumPy array of shape n samples. N features, where n samples is the number of data points and n features is the number of features. N components, the number of dimensions to reduce the data to. Outputs: Y. The lower dimensional embedding of the data is a NumPy array of shape n samples. N components. Reconstruction error: the reconstruction error for each data point, indicating how well the data can be reconstructed from its neighbors in the lower dimensional space. Steps: Find the k nearest neighbors for each data point. Compute the weights that linearly reconstruct each data point from its neighbors. Minimize the reconstruction error in a lower dimensional space by finding the embedding that preserves the local neighborhood relationships as much as possible. Metrics: Reconstruction error measures how well the original data can be reconstructed from its neighbors. In the lower dimensional embedding, lower reconstruction error indicates better preservation of local relationships. Visualization plots: Scatter plot visualize the lower dimensional embedding of the data, showing the relationships between data points. Pairwise scatter plot plot all pairs of dimensions in the lower dimensional embedding to explore potential correlations. Fine-tune parameters: N neighbors, the number of neighbors to consider for each data point. A higher value might capture more global relationships but can lead to overfitting. Reg regularization parameter for the local reconstruction weights. A higher value can prevent overfitting. Eigensolver: the solver to use for computing the eigenvectors of the Laplacian matrix. Auto selects the most efficient solver based on the data size. Method: the method to use for finding the embedding. Standard uses the standard LLE algorithm, while modified uses a modified version that can be faster for larger datasets. Uncertainty methods: Confidence intervals for the embedding estimate the uncertainty in the embedding coordinates by considering the variability in the reconstruction weights. Out-of-sample extension use a similar algorithm to embed new data points into the existing lower dimensional space. Challenges and fixes. Challenge 1: Overfitting to the data. Sample use case: when the number of neighbors is too high or the regularization parameter is too low, the algorithm might overfit to the local structure of the data, resulting in poor generalization to unseen data. Fixes: Reduce the number of neighbors. Increase the regularization parameter. Challenge 2: Computational complexity for large datasets. Sample use case: LLE can be computationally expensive for large datasets, especially when the number of neighbors or the dimensionality of the data is high. Fixes: Use the modified LLE algorithm, which can be faster for larger datasets. Use a smaller number of neighbors. Consider using a different dimensionality reduction technique like tsne, which can be more efficient for high-dimensional data. Challenge 3: Difficulty in handling data with nonlinear relationships. Sample use case: LLE assumes that data points can be linearly reconstructed from their neighbors, which might not hold true for data with complex nonlinear relationships. Fixes: Consider using a different dimensionality reduction technique like tsne or isomap. which can handle nonlinear relationships more effectively. Challenge 4. Sensitivity to the choice of parameters. Sample use case. The performance of LLE can be sensitive to the choice of parameters like a number of neighbors and the regularization parameter. Fixes. Carefully tune the parameters using cross-validation or other techniques to find the optimal settings for the specific dataset.